Okay, we're on to the next section, 11.2 Combinations, Part 1. Let's do a little bit of startup here. As part of the grade 12 acting class course, students are required to read the following 3 plays in a 3-month period. Hamlet, let's call it H. A Christmas Carol, C, and Pride and Prejudice. So let's demonstrate what combinations are all about. Due to previous late returns, Tom is only allowed to sign out 1 play from the school library per month. List all the different orders in which Tom could sign out the plays. So he could sign out Hamlet, Christmas Carol, and Pride and Prejudice in that order, and just rearrange those letters to see the other ways he can sign them out. Now this is where order matters, right? This would be a permutation, right? Tom's friend Sam is allowed to sign out all 3 plays at the same time from the school library. So this is the key here. At the same time, all 3. How many different ways can he sign out all 3 plays at the same time? Well, whether you write HCP or HPC or any of the other ways, really, I'm just going to stick with this one. Only one way. Because if you're signing them all out at one time, doesn't matter if you sign them out HCP, PCH, CPH, you're still signing out all 3 at one time, so only one way. Part A, let's call it A here, is an example of a permutation where order is important. All these 6 orders are important, which order you sign them out in. Part B is an example of a combination, so only one way, where order is not important. Okay, suppose the students in Part A were required to read only 2 of the 3 plays. Complete the table to show the number of ways in which Tom and Sam could do this. So remember, permutations, order matters. Okay, what are the different ways? HC, CH, CH, CP, PC, HP, PH. Okay. How about Sam? Remember, this is a combination, so we're starting a new topic. Order does not matter. So if order doesn't matter, 2 at a time, these are the only ways Sam could sign out the books. Okay, sorry, the plays. So HC, CP, and HP. Those are the only 3 possible ways. Because if you sign that out as CH, well, that's the same as HC, so we need not say that. Same thing here. If you signed it out as PC, it's the same as CP, so we don't need to restate it. You're double counting. Again, PH, nope, because order doesn't matter. PH is the same as HP, so we can just say HP. Complete the following statement. So 6 different ways, 3 different ways. Let's see how they're related. The number of combinations, so number of combinations is equal to the number of permutations divided by 2 or 2 factorial. So if I show a permutation, so in this case, permutation, 6 things, permutation of 6 things taken 2 at a time, that's 3 factorial over 3 minus 2 factorial, and that's just 3 factorial over 1 factorial, and that equals 6. Okay, combination is a selection of elements in which the order of the selection is not taken into account. So if I take 6 and divide it by 6 and I divide it by 2, I get 3 different plays, 2 or 2 factorial. And we'll see a formula shortly that will explain how we get at this number 3 with a proper formula. Next page. Here's our proper formula. Combinations, the notation NCR. So a combination of n things taken r at a time, or another way to the notation is like that, represents the number of combinations of n items taken r at a time where n is greater than or equal to r, okay, and r is greater than or equal to 0. So in our previous example, if I take 3 things taken 2 at a time with a permutation, okay, that equals 6. We saw that, right? And then the combination formula, we divide out the r value. So the r value is 2 factorial. And that's how we ended up getting the 3. Think about this 2 factorial as dividing out all the repeat values, right? The repeat values in the previous example being these values that we talked about, where the order doesn't matter. So now you have to take out the repeat values. Well, how do you take out the repeat values? You divide it out with this factorial in the denominator. And when you simplify, it ends up becoming this. So if I plug this into the formula, so combination of 3 things taken 2 at a time. Okay, so this is example for Sam where there's only 3 ways. So that's 3 factorial over 3 minus 2 factorial times 2 factorial. That equals 6 over 2, and that is 3 ways. Okay, as I mentioned before in class, it is an expectation that you know how to do this on your calculator, whether it's a TI. Also, for you Casio folks, there's a particular way to do combinations, so make sure you know how to do that. Let's do another example. 5 students, Amira, Bilal, Chelsea, D'Agostino, and Ikai are competing in a singing contest. First prize gets $100, second prize gets $50, and third prize gets $25. The following table shows all the possible ways the 5 students can win the 3 prizes. Okay, so A, B, C, D, E, and we've listed out all the different finishing positions in first, second, and third place. Okay, so this example in A represents what? A permutation or a combination? Does order matter? Well, if you're awarding a first, second, and third place, so 1, 2, and 3, of course order matters. Okay, so this is definitely a permutation. How many ways are there to award the 3 prizes? Show this using the appropriate formula. Well, if you count all these, that's 10 in each row. Oops, sorry, that's 6 in each row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There is 6 times 10 equals 60 ways. Or we have 5 students permuted. How many? 3 at a time, 3 places. That's 5 factorial over 5 minus 3 is 2 factorial. 5 times 4 is 20, times 3 is 60. Okay? So that is a permutation. Part B, for participating in the singing contest, the school has been awarded 3 places at a local singing school. 3 students will be selected at random to attend the local singing school. Using the table below, same as above, circle the different ways the 3 students can be chosen. Okay? So now, here's the key here. Order does not matter. Okay, let's be careful here. So if I have, remember, we're just awarding 3 places. We don't care about the order. A, B, C. All of these values contain an A, B, and C, so these are all repeats because we're just awarding 3. We're we're assigning 3 spots. Same thing, A, B, D, doesn't matter. These are all the same. A, B, E, and you can so on and so on. This A, C, D, these all contain A, C, D. So all of these, all the ones on the bottom here are repeats, right? Because, key here, combination. Order does not matter. The example above represents a combination. How many ways are there to select the 3 students? So if we take the permutation from above, right, the formula, 2 ways to show it. Oops. Permutation from above, 60 divided by 6. Okay, that equals 10. Or if we use the combination formula, so there's 5 students. How many ways can we group them into 3? So a combination of 5 things taken 3 at a time. 5 factorial, 5 minus 3 factorial, 3 factorial. Okay. Okay, and then I get 20 divided by 2, and that equals 10. All right, there we go. Complete the following statement. The number of combinations is equal to the number of permutations divided by 6 or 3 factorial. Okay, let's go over some examples. Example 1. So examples of combinations. So determine how many ways the debating club coach can select a team from 6 grade 11 students. So 6 grade 11 students and 7 grade 12 students if the team has 4 members. So I have 13 members total. 13 total. This is important. So 4 members, no restrictions, just 4 members, right? So out of the pool of 13, remember, order doesn't matter. I'm just selecting 4 members. So it's a combination of 13 things, taken 4 at a time because I need 4 members. So for now, what I'm going to do is I'm going to write out the formula so you get used to practicing it. So 13 factorial over 13 minus 4 factorial, 4 factorial, right? And then you can practice reducing it. That's 9 factorial, 4 factorial, and then the rest you can just use your calculator, okay? In the future, you can just type this in directly into your calculator and just grab that value, okay? 4 members, only one of whom is in grade 11, okay? So one of whom is grade 11. So grade 11 students, I have 6, combination of 6 things, and I just need 1 student. So this is grade 11. Okay, and then the rest times, we need the rest to be grade 12 students, right? So how many grade 12 students can we select from? So a combination of 7 things taken, right? We have 1 grade 11 student here, and we need 4 remaining grade 12 students. And again, order doesn't matter, so it's, we need 3 remaining grade 12 students. So it's a combination of 7 things taken 3 at a time. Do that directly into your calculator, I get 210. Okay, 4 members, part C. And the debating team's coach's daughter, who is a grade 12 student, must be on the team. So coach's daughter, that's grade 12. So there's only one way to assign that one position. So it's a combination of one thing taken one at a time times, well, after we take out one of the members, remember we have 13 total, we take out one of the members, we only have 12 to select from, so a combination of 12 things, and then 3 remaining slots. No restrictions, can be grade 12 or 11, so we have a pool of 12, and we need to select 3. Remember, order doesn't matter. This one, let's do out longhand here, so a combination of one thing taken one at a time, so 1 minus 1 factorial 1 factorial times 12 factorial over 12 minus 3 factorial 3 factorial. All of this 1 factorial over 0 factorial 1 factorial, it's going to end up equaling 1. So 12 factorial over 9 factorial 3 factorial, this is just 1. And that ends up being 220. So 220 ways to form a team of 4 members where the debating team's coach's daughter is on the team, and then the rest of the 3 members, there's no restrictions. Okay, example 2. Combinations with cases. An emergency response team of 4 people is selected from a group of expert volunteers consisting of 2 doctors, 3 surgeons, 3 firefighters, and 4 nurses. Determine how many ways the team can be chosen if it must contain one type of each volunteer. Okay, so 4 members in the team for all these examples. Okay, so let's keep that in mind. We have 4 members to select, one type of each volunteer. So we have 2 doctors, 3 surgeons, 3 firefighters, and 4 nurses. Okay, one type of each volunteer. I'm going to start with the doctors. So there's 2 possible doctors, a combination of 2 things taken. We just need 1 doctor. So this is doctor. For the surgeons, there's 3 possible surgeons. I just need 1. So this is the surgeon. Firefighter, likewise, 3 possible firefighters. I'm just selecting 1. And the last one is 4 possible nurses. I'm just selecting 1. So this is a nurse. Put that all in your calculator. I got 2 times 3 times 3 times 4. And that's 72 possible ways to pick a team of 4 where it's 1 of each volunteer. How about exactly 2 firefighters? Okay, the pool of firefighters, I have 3 possible firefighters. I need to select 2. This is exactly 2. Someone is exactly 2. And then the other 2, there's no restrictions. So after you take out 2 members, oh, here we go. 2 plus 3 is 5, and 3 is 8. 8 and 4 is 12 total. There's 12 total members. Okay. These remaining, so this is firefighter. These remaining 2 positions, I only have 9 to select from because that 3rd firefighter that's not selected in the first 2, I can't use them again because I said exactly 2 firefighters. So it's only 9 left. Okay, 12 minus 2 is 10, but that one of those is a firefighter, so I have to take that out. So 9, combination 9 things taken only 2 at a time. So the remaining 2, I can choose any. Okay, so that's 3 times 36, and that equals 108. How about at least 2 firefighters? Okay, at least 2 firefighters. At least 2 means 2 firefighters. 3 firefighters, or all firefighters, 4, right? If you mean at least 2, I can have 2 firefighters, 3, or 4. So that fits that definition. So similar to an example we did with permutations, we have to list out all the cases and we have to add them all up. So case 1, 2 firefighters, and I'm just going to borrow that from B. So from B, what we just did, that equals 108. So we're not going to do any extra work, okay? Case number 2, 3 firefighters. So I'm going to modify this equation here, or that combination. So 3 things, combination of 3 things taken 3 at a time, that's 3 firefighters, times, okay, how many remaining? So 12 minus 3 after you select the 3 firefighters, that's 9 left for the remaining, not 2 positions, but 1 position, 4-member team, right? So case 2, that is 1 times 9, and that equals 9. Okay, so let's just circle that so far. And case 3, 4 firefighters. Well, how many ways are there to select 4 firefighters? Let's do the math. And so can we select 4 firefighters? Well, let's take a look. Only 3 available, right? So there's no way to select 4 firefighters, so our answer would be the addition of those 2, that's 117. 117 possible ways to select at least 2 firefighters. So let me just scratch this out. There is no way, it's kind of a trick question, there is no way to select 4 firefighters because we don't have 4 firefighters. Okay, letter D, at most 2 surgeons. Okay, so at most, well, what could that mean? That could mean 1 surgeon. Oh, let's start from the bottom here. 0 surgeons. 1 surgeon. Or 2 surgeons. So we have to be careful on the language here. At most, we've listed out 3 cases. Okay, let's do case 1. 1 surgeon. Oops. 0 surgeons. Okay, if it's 0 surgeons, we don't want any surgeons. Take out the surgeons. That's 12 minus 3. So I have a pool of 9 to select from. 9 things taken 4 at a time. So a combination of 9 things taken 4 at a time, just on my calculator, I have 126. Okay, so let's set that aside, case 1. Case 2. 1 surgeon. I have 3 possible surgeons. I'm selecting 1, multiply it by the remaining members that I can select from. Again, no surgeons, or actually just 1 surgeon, so I have 9, and I'm selecting 3 more positions. So that's 3 times 84 equals 252. Let's circle that, circle that. Case number 3, 2 surgeons. Okay, 3 surgeons again for 2 slots. And then the remaining 9 folks, I'm selecting only 2 this time. So that's 200, oops. That is 3 times 36 equals 108. Okay. And then let's add those 3 up. 126 plus 252 plus 108. 126 plus 252 plus 108. I get 486. 486 possible ways to select at most 2 surgeons. Okay, exactly 1 firefighter, letter E, exactly 1 firefighter and 1 doctor. Okay, how many ways to select 1 firefighter? Well, I have a pool of 3 of them, combination of 3 things, and I just need 1. Okay, 1 doctor. I have 2 possible doctors, combination of 2 things taken, just 1 at a time. And then the remaining, it says exactly 1 firefighter, 1 doctor, right? So I'm just looking at surgeons and nurses. Well, how many surgeons and nurses? 3 plus 4, so I have a pool of 7 to pick from, and I need only 2 more slots filled, right? So 7 to pick from, 2 more slots filled. So that's 3 times 2 times 21, and that equals 126. Okay, next page. So combinations problems. I love these problems that deal with a standard deck of playing cards. And we'll also look at the ones that deal with at least and at most again. Here's some key characteristics of a standard deck of 52 playing cards. If you've never played cards, here are the basic characteristics. There's 4 suits. Spades, clubs, diamonds, hearts. So these are spades, clubs, diamonds, and hearts. 2 red suits, so red, hearts and diamonds are red, and 2 black suits, clubs and spades are black. With numbers from 2 to 10, so the numbers from 2 to 10, an ace, the letter A, and then I have face cards, which have the letter J, Q, and K for Jack, Queen, and King. Okay, so you got a quick overview of what cards are. And note there's each suit has 13 cards. So 13, 13, 13, 13. And you can tell here that the cards come in groups of 4. So there's 4 3s, 4 8s, and so on. Okay? All right. Let's give this a try. Determine how many 5-card hands can be formed if there are no restrictions. So I'm picking from a pool of 52 cards, a combination of 52 things taken 5 at a time, 5-card hand. So 52 factorial over 47 factorial, 5 factorial, that is a whole lot of ways, 2,598,960. Okay, part B, what if all the cards are spades? So spades, here are my spades here, folks. Okay, I have 13 of them. So I have 13 possible cards to choose from. So it's a combination of 13 things taken 5 at a time, 5-card hand. Okay, so this is possible spades. And then this is 5-card hand. Okay, that equals 13 factorial over 8 factorial, 5 factorial. That is only 1,287 possible ways to make a 5-card hand with only spades. Okay, letter C. The 5 cards are of the same suit, so I'm just going to clean this up just a bit here. Okay, same suit. So the previous one we just did in letter B, they're spades, right? So we found that there's 13, combination of 13 things taken 5 at a time. That's just for the spade. So this is for 1 suit. Oops. 1 suit. but there are 4 suits. I'm just going to multiply by 4. So 4 suits, and that equals 1287 times 4, and I get 5,148. Okay. Ooh, how about this one? Letter D. Determine how many different 5-card hands can be formed if there's exactly 2 pairs. Well, here's an example of 2 pairs. If I have a 2 and a 2, a 4 and a 4, and then just something else for the 5th card, right? Another one, K and a K, J and a J, 2 pairs of kings, or sorry, pair of kings, pair of jacks, and the number 6, right? Another one, ace, ace, 4, 4, 9. This is not 2 pairs. So if I do this, if I have 4 queens in a standard game of poker, or just a deck of cards, this is 4 of a kind. This is not 2 pairs. I know there's 2, but they're all the same. They're all the same rank, right? So we need different pairs, right? We can't do 4 of a kind. Okay, so let's set that as a premise, and let's do exactly 2 pairs. Well, if we're doing exactly 2 pairs, the first thing I need to do is select the ranks. Okay, so I'm going to select the ranks first. So select where they're coming from, right? So 13 things taken 2 at a time, right? So out of a particular suit of cards, I'm going to pick the ranks, okay? And then I need to select the first pair. Okay, so out of that rank, I'm going to select the first pair, which is, I don't know, there's 4 possible cards per value, right? So, and then I'm going to select the second pair. Same thing. Okay, and then the 5th card. I have 44 cards left, right? So I've selected 2 pairs, so that's 4 cards. So 52 minus 4 is 48. And then I don't want to select any more of the other cards that will pair up and make a triple of the first pair or the second pair, right? So I have to take out 4 more cards. So I'm taking out 8 cards, so I have 44 left. Okay, and then that is 5th card. Right, so here's an example. I'm going to select the 2 ranks, right? Within one of the suits, okay? And then I'm going to select the pair. So let's say I select 2 and 2, and I select queen and queen. Well, the other 2 and the 2 and the other queen and the queen, I don't want to select for this 5th card. So that's 52 minus these 4 minus these 4 that I've already selected, and that's 44. Okay, so that's how I get 44. Okay, all of this, that's 78 times 6 times 6 times 44. I get 123,552. Okay. There's at least 1 red card. Okay. So if I do this at least 1 red card, well, I can have 1 red card, 2 red cards, 3 red cards, 4 red cards, 5 red cards. Well, and then add those up, that's too much work. Let's do it a simpler, faster way. Okay. Find number of hands with no reds. Okay, and then B, find number of hands with no restrictions, which we found in the very first part example. Okay, no restrictions. And then do A minus, and then do B minus A, and then we'll find number of hands at least one red. Okay, does that make sense? Okay, let's do the example here. Okay, no reds. So we know that 2 of the suits are red, so that's 26 cards that are red. So 52 minus 26. I have 26 remaining cards to pick from. I need a 5-card hand. So 65,780 possible 5-card hands where there are no red cards. No restrictions. This is actually from part A, so that's 52 cards taken 5 at a time. 2,598,960. So if I do 2,598,960 minus 65780, I get 2,533,180 hands with no, with at least one red. Okay, there are at most 2 queens. Okay, so this one, let's find hands with no queens, 1 queen, 2 queens, and that'll meet the definition, and then add. Okay, and that'll meet the definition of at most 2 queens. Okay, so case 1, no queens. That is, if I'm selecting no queens, I need to do 52 minus 48. 52 minus 4 queens, so I have 48 to select from. Combination 48 things taken 5 at a time. Okay, 1 queen. Okay, so this time I'm selecting 1 queen. I have 4 queens to select from. I'm only selecting 1 times 48 remaining cards. I'm selecting 4 more. Okay, there's the number of hands, number of 5-card hands with at least 1 queen. Sorry, with exactly 1 queen. Last one, 2 queens. 4 queens to select from. I'm selecting 2 cards. Okay, 48 remaining cards to select from. I'm selecting how many? 3. Okay, and then there are 103,776 possible 5-card hands with exactly 2 queens. So let's add these 3 up. That's 1712304 plus 778320 plus 103,776. Add them all up, I get 2,594,400. What is this? Possible 5-card hands with at most 2 queens. Okay. So I do have to say this one thing. This example, let's say here's a possible for letter F. There's a possible hand at most 2 queens. So let's say that we have queen, queen, 6, 5, 3. Okay, let's say that's our hand. This is a combination. So when we're selecting possible hands, 5-card hands, remember order doesn't matter. Order doesn't matter. So queen, 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 6, 5, 3. It's the same hand as, let's say we selected it this way, queen, 6, 5, queen, 3. It's still the same cards, but the order doesn't matter because we just want to see how many ways you can select a queen, queen, 6, 5, and a 3. So it equals this, right? So when you're doing your combination formula, this part here, the r factorial that you're dividing out, right? In this case, it will be 5. You're dividing out all of these repeats. I call them repeats in that the order doesn't matter, right? So here's another repeat, Q, 6, 3, 5, Q. This is another repeat. Well, when we divide it out by r factorial, this 5 factorial, we're taking care of or accounting for all the repeats so we don't overcount. We just want to count the one unique case here.